Hi everyone, part 3, electric fields. An electric field, so let's define it first. An electric field is simply the space around a charge that is affected by that charge. The effect produced, of course, is a force. An electric field is a vector quantity, so both magnitude and direction are required. Okay. Other examples of vector fields include gravitational and magnetic fields. You have experience with gravitational fields. Gravitational field, we are all caught in Earth's gravitational field. It is the effect that pulls us downward. Okay, remember it affects or creates the gravitational force. Okay, and the gravitational force is always attractive for gravity, so we are attracted to the center of the Earth. Magnetic forces, okay, we'll deal with those next section. Okay, scalar fields include sound and temperature. Imagine yourself sitting around a campfire. Okay, you are influenced by the heat of the fire. That is a heat field. Okay, now the further you get away from the fire, the less you feel its effects. Okay, so that is the heat field there. Electric fields work very similar. The further you are away, the less the field affects you and the less the force is. Okay, so magnitude and direction of an electric field. Okay, it is dependent upon the charge of the object, and how we say that is we say it's the direction that a small positive test charge will react once inside the field. So the test charge is always positive, and the source charge could be positive or negative. Okay, so let's have a quick look. If I draw a negative charge, okay, and I drop a little positive guy right there, which direction is he going to go? Oh, a positive and a negative attract, so that positive charge is going to go inward. So around a negative source charge, we say the electric field goes inwards towards the negative charge. Okay, if we have a positive charge, okay, and drop another little positive test charge, which way is that test charge going to go? Well, it's going to repel. So we say that for a positive source charge, the electric field is going outward. Okay, now we do have a little bit of experience with this because remember, if we have the Earth, okay, and its gravitational field was always pulling down, right? The people in Australia don't fall off the Earth, right? They are still attracted to the center of the Earth. Okay, so a gravitational field looks a lot like a negative charged electric field, or the electric field around a negatively charged object. Okay, again, a positive charge, okay, that has an electric field going outward. Okay, now to calculate this field strength, okay, so we use the formula E. So E stands for the electric field strength, okay, and that is in newtons per coulomb or volts per meter. Both of them work. Okay, Fe, of course, is the electric force, and Q is the magnitude of the test charge. Now, when you look at this formula, does that remind you of anything? Okay, wouldn't necessarily be this, would it? Fg over m. See, that formula is very similar to the gravitational field strength that you learned in Physics 20. Okay, so E is the electric field strength, Fe, of course, is the electric force, and Q is that charge. Well, remember, G was the gravitational field strength of Earth, okay, in newtons per kilogram, okay, which also happened to be meters per second squared. Fg was the force of gravity, and m was the mass. So this is very similar. You guys have done these formulas before, just we used masses and gravity last year. Now we're using electrics. Okay, so next page, practice problems. An ion with a charge of that is placed in an electric field produced by another larger charge. If the magnitude of the field at this position is that many, so 1,000 newtons per coulomb, calculate the magnitude of the electrostatic force on this ion. Okay, so we want the force, so our formula is E equals Fe over Q. So we can rearrange that. So Fe equals EQ. All right. Okay, so the E is 1.00 times 10 to the 3 newtons per coulomb. Sorry, 10 to the positive 3. I think I said negative. Anyways, doesn't matter. So positive 3 newtons per coulomb times the charge, 1.60, times 10 to the negative 19 coulombs. Okay, and when we type that in, oh look, we get 1.60 times 10 to the negative 16 newtons. Okay, awesome. So remember, so that you can figure out the force on this, some questions will ask you to figure out the acceleration at this point. Well, of course, we know that formula F equals ma, right? So if I wanted to figure out the acceleration on this, of course, they would need to give me the mass of this charge and probably a direction then too. Right now, it just wants the magnitude, okay? The magnitude is just the size of the force, not the direction of the force. They need to give us more information. But again, some questions ask for acceleration, in which case you just divide the force by the mass. All right, moving on. Number 2, the magnitude of the electrostatic force on a small charged sphere is 3.42 times 10 to the negative 18 newtons. When the sphere is at a position where the magnitude of the electric field due to another charge is 5.34 newtons per coulomb, what is the magnitude of the charge on this small charged sphere? So this time I'm looking for Q. So again, the formula on our formula sheet is E equals Fe over Q. So this time I'm looking for the Q. So those guys just change places. So Q equals Fe over E. Okay, so the force was 3.42 times 10 to the negative 18 newtons, and the electric field was 5.34 newtons per coulomb. Okay, and when we type that in, we end up with a charge of 6.40 times 10 to the negative 19 coulombs. And there you go. So that's that one. Now, there is another force for electric fields. So alternatively, electric field strength can be calculated using this formula. So E equals KQ over R squared. Okay, where E is the electric field strength, again in newtons per coulomb or volts per meter. Q is the magnitude of the source charge this time. Okay, R is the distance from the center of the source charge to any specific point. Okay, that's measured in meters. And K, of course, is Coulomb's constant, that whole 8.99 times 10 to the 9 thing again. Okay, now hopefully this formula also looks familiar, because remember, electric field strength is just like gravitational field strength. And remember last year that was big G M1 over R squared. Okay, and remember this, to figure out the gravitational field strength of Earth, we used the mass of Earth. And when we typed in all those numbers, we ended up with 9.81 meters per second squared, or of course newtons per kilogram. Okay, so this formula is very, very similar to that. It's just the E is electric field strength. Okay, it has the absolute value bars around them because this could be either positive or negative, and it depends on that source charge. Remember, negative charges, the electric field always goes inward, and positive source charges, the electric field always goes outward. Okay, so we will have to figure that part out as we go. Okay, so practice problems for these ones. Number 1. The electric field at a position 2 centimeters from a charge is 40.0 newtons per coulomb directed away from the charge. Determine the charge producing the electric field. Okay, so look, I've got this charge, and I don't even know if it's positive or negative yet, but we'll get there. Okay, electric field 2 centimeters away from it. So let's say 2 centimeters, let's put that there. So this is 2 centimeters or 0.0200 meters. Okay, and it is directed away from the charge, so it's going this way. Oh, wait a second. If it's going away from the charge, oh, look, that's going to be a positive charge. So whatever my answer is, it's going to be, for the Q, it's going to be positive because the electric field is going away from the charge. All right, so let's figure that out. Okay, so electric field is equal to KQ1 over R squared. All right, so we know that the electric field is 40.0 newtons per coulomb. Okay, K is 8.99 times 10 to the 9th newtons meters squared per coulomb squared. Okay, times Q1, which we don't know what that is. And then R is 0.0200 meters. Remember, that has to be in meters for this to work. Okay, and then Q equals, or Q1 equals. Now, we've already said that this is a positive charge. Okay, so we know that if it was a negative charge, we would just put a negative there. Our calculations aren't going to say positive or negative. We just have to interpret what they mean. Pardon me, I guess the calculation will always be positive, but we have to figure out whether the charge is positive or negative based on the direction of the field. All right, so we type all this in. So 40 times the 2 divided by, or times the 2 squared, divided by the 8.99 times 10 to the 9, and we end up with 1.78 times 10 to the negative 12 coulombs. Okay, we've already said that that's a positive charge because the electric field is going away. So there is our final answer. Yay! Number 2. An electron has a charge of that. At what distance from the electron would the magnitude of the electric field be 5.14 times 10 to the 11 newtons per coulomb? Oh, at what distance? So this time I'm looking for the R. Okay. Now remember, this is a negative charge, so that electric field is going to be directed inward towards the electron. Okay? Because the electric field always goes towards negatives. Anyways, so electric field is equal to KQ1 over... Wow. Let's try that again. KQ1 over R squared. So 8.99. Whoops. All right, so let's figure this out. Okay, so the electric field, we want to be 5.14 times 10 to the 11 newtons per coulomb. Okay, K is 8.99 times 10 to the 9th newtons meters squared per coulomb squared times the charge, so 1.60 times 10 to the negative 19 coulombs, all divided by R squared. Okay, so remember that those just switch places, and then we square root to get the R. Okay, and when we type all that in, we get 5.29 times 10 to the negative 11 meters. Okay, so very, very small distance, but the numbers are what they are. Don't stress over that part. Number 3. This is dealing with collinear field vectors. Now, just like last section when we added or subtracted electric forces to get a net force, now we might have to add or subtract electric fields. Okay, so if we have a quick look, and collinear, of course, means along a line. Okay, so these are easier than the non-linear ones, which we'll get to here in a second. So, number 3, calculate the net electric field at a point 2.10 times 10 to the negative 2 meters to the left of the 1.50 times 10 to the negative 6 coulomb charge in the figure below. Okay, so the 1.50, that's this charge here, and I need that to be 2.10 times 10 to the negative 2 meters to the left. So really what I'm trying to find, everyone, is the electric field at that point right there. And that is 2.10 times 10 to the negative 2 meters away from that electric field. Okay, so let's just have a quick look at what's going on. These are positive charges, so the electric field, because of this positive charge, is always going to be going outwards. Okay, so the electric field at this point is going to be going to the left. Okay, awesome. Now look, this other charge, now he's quite a bit further away, so his electric field is not going to influence as much as the first charge. However, he is still going outward. So at this point, way over here, this second charge will still exude a rightward force on that point, or a rightward field at that point. Okay, so we're going to end up figuring out two electric fields with two distances, and we're going to end up adding them together because they're both going in the leftward direction. Okay, so, well, first things first, let's do the first one. So the electric field, because of that first guy, is KQ1 over R squared. So 8.99 times 10 to the 9th newtons meters squared per coulomb squared. And the first charge is 1.50 times 10 to the negative 6 coulombs, all divided by 2.10 times 10 to the negative 2 meters squared. Okay, so when we figure out this one, okay, let's get the calculator out. So 8.99 times 10 to the 9 times 1.5 times 10 to the negative 6 divided by 2.1 times 10 to the negative 2 squared. Okay, so this one works out to 3.0. Let's see, I've got 3 sig digs everywhere. Yep, so 3.06 times 10 to the 7. Okay, and this, of course, is newtons per coulomb. Okay, so that's that electric field, and we know that that is directed to the left because it's a positive charge, and we're going away from the positive charge. Now we figure out the second one. So the electric field strength here, KQ1 over R squared, I guess we could call that Q2. The subscripts really don't matter. So 8.99 times 10 to the 9th. Newtons meters squared per coulomb squared times this guy is 2.00 times 10 to the negative 6 coulombs. Now this distance, though, they're 3.3 times 10 to the negative 2 meters apart in themselves, and then we go another 2.10 times 10 to the negative 2 out to the side. So that works out to 5.4 times 10 to the negative 2. 0.40 times 10 to the negative 2 meters. So that is the total distance. That is the total distance from this charge to that point. Okay, it's going to be quite a bit smaller because, of course, well, it's got a slightly bigger charge, but the distance plays a huge role in these kind of questions. So 8.99 times 10 to the 9 times 2 times 10 to the negative 6 coulombs divided by 0.054 or 5.4 times 10 to the negative 2 squared. Okay, and then this guy works out to 6.0 6.17, there we go, 6.17 times 10 to the 6th newtons per coulomb. Okay, again, we're going to use all our digits later on. Again, this is directed to the left. Awesome. So, look, it's quite a bit smaller, right? A whole power of 10 smaller. Okay, not a big deal. So then the net electric field, net or resultant, okay, we know that they're both going left, so we just add them. So 3.06 times 10 to the 7th newtons per coulomb plus 6.17 times 10 to the 6th newtons per coulomb. Okay, so when we add those together, we end up with 3.67 times 10 to the 7th newtons per coulomb left. And that is our final answer. Perfect. All right, moving on. Number 4, an electron and proton are 5.29 times 10 to the negative 11 meters apart in a hydrogen atom. Determine the net electric field at a point midway between the two charges. Oh, wow. Okay, so we've got a positive charge here, so the proton, and a little tiny electron there. Okay, definitely not to scale, but don't worry about it. Okay, now we need the electric field at the point midway between them. So midway, of course, is going to be 5.29 times 10 to the negative 11 meters divided by 2. So this is where we're going to figure out the electric field at. So that is 2.65 times 10 to the negative 11 meters. Awesome. Okay, now at this point in space, the electric field from the proton is going to be pushing outward. Okay, now the electric field from the electron, oh, look at that, is going to be pushing or pulling inward. So we're going to have two electric fields, but the direction are both to the right. So we're going to take these electric fields and we'll add them together in the end. Okay, so let's see, we'll do the electric field for the proton first. So KQ1 over R squared. So 8.99 times 10 to the 9th newtons meters squared per coulomb squared. Okay, Q1 is, now, it doesn't tell us the charge of the proton. Oh goodness, what are we going to do? Okay, those numbers are on the back of your formula sheet, remember? Okay, they're also in your notes from earlier on, but they are on the formula sheet, so you always have them. So the charge of a proton is 1.60 times 10 to the 19th coulombs. Sorry, negative 19 coulombs. And we figured out this distance to be 2.65 times 10 to the negative 11 meters. And of course, that is squared. Okay, so when we type that in, we get 2.06 times 10 to the 12th newtons per coulomb. Okay, so now we figure out the electron, the electric field because of the electron. And hey, wait a minute. When we figure out, or when we look on the back of our formula sheet, the 9 newtons meters squared coulomb squared, hey, the charge of an electron is still 1.60 times 10 to the negative 19 coulombs. Hey, wait a minute. That means that's going to be the same number, 2.65 times 10 to the negative 11 meters squared. Hey, those are the same numbers, yeah, so it's going to be 2.06 times 10 to the 12 newtons per coulomb. Wow, that's crazy. But remember, proton and an electron have the same charge. Okay, the only thing that's different is the direction of the electric field out of the positive or out of the proton. The electric field goes out or away from the proton, and in the electron, the electric field goes towards the electron. Now, in our drawing, we can see that they're both going in the same direction. Now, look, even if I drew the electron up here somewhere, okay, at that point, we'd be going outward from the positive and towards the negative, so that would still count as collinear in a straight line, so we just simply add the two electric fields together. So the electric field net, so 2.06 times 10 to the 12 newtons per coulomb plus 2.06 times 10 to the 12 newtons per coulomb. So that works out for us to be 4.11. Remember, use all your digits, because if you just did 2.06, you'd get 4.12. But remember, use all your digits, so it's only 4.11 times 10 to the 12 newtons per coulomb. And in our little picture here, it's directed to the right. Now, if you drew your picture different, then you could say left. You could also say towards the electron or away from the proton. All of those words are appropriate. Okay, so because my picture went that way, I'm just going to say to the right. Okay, so number 5, non-collinear vector fields. So this means these are not in a straight line anymore. Okay, so number 5, calculate the net electric field at point P, which is 0.1 meters from two similar spheres with positive charges of 2.00 coulombs and separated by a distance of 0.0600 meters as shown in the figure. Okay, awesome, great. So I want this field right there, the electric field at that point. Now remember, these are both positive charges, so the electric fields are going to be directed away at this point. Now, funny thing, these are the same charges, the same angles, the same distances, everything. So just really quick, we're going to resolve that vector into an X electric field and a Y electric field. So EX and EY. Now, it makes sense that these numbers would be the same because they're the same charge and the same distance. So if we draw the other one, EX and EY, okay, we get that one. Now I want you guys to take particular note of the EXs. Look, we've already discussed these are going to be the same numbers, so what's going to happen to the electric field in the X direction? Look, they're going to be the same numbers, but one is going to the right and one is going to the left. The X direction ones are going to cancel each other off. Okay, very cool how that works. Now, it doesn't always work that way, because as soon as I change the charges or the angles or anything like that, then it wouldn't work. But in this case, it would. Anyways, that completely aside, let's figure out the electric field for the first one. So that's KQ1 over R squared. So 8.99 times 10 to the 9th newtons meters squared per coulomb squared. Okay, so times 2.00 coulombs, all divided by 0.100 meters squared. Okay, now it makes sense that this number would be the same for both of these things, and of course it is, but that's okay. So 1.80 times 10 to the 12 newtons per coulomb. So that's the numbers that we're working with. Okay, now let's resolve these into X and Y vectors. Okay, so we know that we're going to make this triangle here, so we know that this is 1.80 times 10 to the 12 newtons per coulomb, and that is 72.5 degrees. So let's see, sine is going to be the EY. So sine of 72.5 degrees is the electric field in the Y direction. That's 1.80 times 10 to the 12 newtons per coulomb. That is a 12, everyone. Okay, so then the electric field in the Y direction, okay, when we figured that out, so EY, so 1.80 times 10 to the 12 times sine 72.5, so that is 1.71 times 10 to the 12 newtons per coulomb. Now, just for the fun of it, let's figure out the EX. So cosine of 72.5 degrees equals wow. Sorry, I'm trying to write fast, and that's just not helpful. So EX over 1.80 times 10 to the 12 newtons per coulomb. Okay, so EX, that ends up being 5.41 times 10 to the 11 newtons per coulomb. Okay, we should put directions. So this guy is up or north. Okay, and this guy is to the right or east. So right. Okay, fair enough. Now, I could do these whole calculations again if I wanted for this triangle, for the second charge, but we know that the numbers are all going to be the same. The EY is going to be 1.71 times 10 to the 12 newtons per coulomb up. But this time the EX is going to be 5.41 times 10 to the 11 newtons per coulomb left, right? Because that's the component here. We've already talked about the Y. So when we do this, when we figure out the net electric fields for the Y and X direction, so EY total, or resultant, or whatever, so that's 1.71 times 10 to the 12 newtons per coulomb plus 1.71 times 10 to the 12 newtons per coulomb. So that one works out to, using all your digits, 3.43 times 10 to the 12 newtons per coulomb up. And then, of course, EX is going to be 5.41 times 10 to the 11 newtons per coulomb minus 5.41 times 10 to the 11 newtons per coulomb. Oh goodness, so the EX works out to 0, which is exactly what we said it would, but I just wanted to show you the calculations. So of course, if there's no X component, we don't have to draw a triangle for this. We just know that the electric field net is going to be just the upward component, so 3.43 times 10 to the 12 newtons per coulomb up. Okay, we don't have to do a triangle because, of course, there is no sideways component. Awesome. Okay, closing in on it. Number 6. Two charges, 4.00 coulombs each, are placed at the vertices of an equilateral triangle of 2.00 centimeters, as shown in the figure below. Determine the net electric field at the third vertex of the triangle. So right here. So this time, we're just going to take my word for it. We're not even going to bother with the X calculations, because we know that because these are the same charges, the X direction ones are going to just cancel each other out. So I showed you last time that it actually worked out that way. Here, we're just gonna go with it. Okay, remember the electric field will be exactly the same for both directions, both going outwards because it's a positive charge. Okay, so the electric field at these points, KQ1 over R squared. So 8.99 times 10 to the 9 newtons meters squared per coulomb squared times 4.00 coulombs, all divided by 0.0200 meters. Remember, you have to turn the centimeters into meters. Okay, squared. So when we figure this one out, it works out to 8.99 times 10 to the 12 newtons per coulomb. And remember, these these are both going to be away from the positive test charges. Okay, so now we know that we have to resolve these vectors, so we are going to do this. So that is the 8.99 times 10 to the 12 newtons per coulomb. This is 60 degrees for the equilateral triangle. Okay, this one would be EX, but we know that's going to cancel, so we're not going to bother doing that this time. Okay, so that's going to be, so EY is going to be sine. So sine of 60 degrees is going to be the EY over 8.99 times 10 to the 9 newtons per coulomb. Okay, perfect. Okay, so EY in this case. All right, let's figure that out. Okay, 8.99. Sorry, guys, 8.99 times 10 to the 9. Sorry, 8.99 times 10 to the 9 times 4 coulombs divided by 0.02 squared. Oh goodness, I made a mistake here. Sorry, so if you've been following along, so that's 8.99 times 10 to the 13 newtons per coulomb. Oh, I'm sorry. Okay, whatever, easy fix. Well, what just happened? Come back. Okay, so 8.99 times 10 to the 13. Okay, easy fix. Sorry about that. Okay, and then of course times sine 60. So times sine of 60. Okay, right, because that just multiplies up. So the EY here is equal to 7.3 sig digs. We've got 7.79 times 10 to the 13 newtons per coulomb. Awesome. Now remember, these calculations are going to be the same for the other guy. The x's are going to cancel, and then we're going to get two y ones, or y electric fields going in the same direction. So the electric field in the y direction is going to be 7.79, times 10 to the 13 newtons per coulomb, plus 7.79 times 10 to the 13 newtons per coulomb. So that is going to work out to 1.56 times 10 to the 14 newtons per coulomb up. Okay, hopefully you followed the shortcuts there. We didn't do the math on the second charge because the math on the second charge is going to be the same as the math on the first charge. So the two y components are just going to add, the two x components would subtract, and there we go. All right, last one, number 7. Calculate the electric field at a point P that is 4.00 times 10 to the negative 2 meters from a small metal sphere A with a negative charge of that, and 3.00 times 10 to the negative 2 meters from another similar sphere B with a positive charge of that. Oh goodness. Okay, so this is going to be a lot more calculations. That's okay. I didn't leave myself an awful lot of room here, but you know what? I'll try. Okay, so we end up with, let's look at the fields first. This field A is a negative 2.10. So the electric field is going to be coming in at this point. For the B charge, that's a positive charge, so the electric field is going to be coming out. So it's going to be going in this direction. Okay, so our electric fields are going to be kind of all over the place. That's okay. We're going to split them up into x and y directions, and we'll see how it goes. Okay, so the first thing we have to do is we have to figure out the electric field between A and point P. Okay, so the electric field because of A is KQ1 over R squared. So 8.99 times 10 to the 9th newtons meters squared per coulomb squared times 2.10. Remember, we don't put the negatives into these. We've already considered the negative by drawing that arrow going towards object A. Okay, and that is 4.00 times 10 to the negative 2 meters away. Okay, so the electric field here is 1.18 times 10 to the 7 newtons per coulomb towards A. It's towards. Okay. So now let's figure out the electric field because of B. The electric field because of B, again, KQ over R squared. So 8.99 times 10 to the 9 newtons meters squared, coulomb squared, per coulomb squared. Okay, times 1.50 times 10 to the negative 6 coulombs, all divided by 3.00 times 10 to the negative 2 meters squared. So this guy has an electric field of 1.50 times 10 to the 7 newtons per coulomb, 7 newtons per coulomb, and this is away from B. Okay, awesome. So now let's split these two vectors up into their x and y components. So looking at this guy at point P, I have an electric field that is going away at 1.18 times 10 to the 7. Okay, so that's just fine. Here, you know what? I think I'll draw it from point A here. So we go this way and this way because we have this angle, right? 36.9 degrees. Okay, so if I'm going this way, my electric field will go down and to the right. So this will be EY, this will be EX. Awesome. So sine is opposite over hypotenuse. So sine of 36.9 degrees will be my EY over 1.18 times 10 to the 7 newtons per coulomb. Okay, so my EY here, okay, solving for that, EY sine 36, okay, so that is 7.08 times 10 to the 6th newtons per coulomb, and this is being directed down. Okay, cosine 36.9 degrees is going to be my EX over 1.18 times 10 to the 7 newtons per coulomb. So here the EX is going to be cos 36.9 times 1.18. Okay, so that is 9.44 times 10 to the 6th newtons per coulomb. And that one is being directed to the left. Awesome. So that's A. Whew, that's intense. All right, so now we're going to do the same thing. We're going to split the x and y's up for B. So, of course, on B, we have the electric field going out this way. So that's the 1.50 times 10 to the 7 newtons per coulomb. So that goes this way and that way this time. So you can see the electric field is directed to the left. Okay, and the electric field in the y direction is being directed up. Okay, awesome. So that angle is 53.1 degrees. So, okay, so sine would be, so sine 53.1 degrees is EY over 1.50 times 10 to the 7 newtons per coulomb. So EY in this case, 1.20 times 10 to the 7 newtons per coulomb. Okay, and that of course is being directed up. And then cosine of 53.1 degrees, that's going to equal our electric field in the x direction over the 1.50 times 10 to the 7 newtons per coulomb. So EX then, sorry my 28 page number is getting in the way, doesn't matter. Okay, so that works out to 9.00 times 10 to the 6th newtons per coulomb, and this is directed left. Awesome. Now the reason I'm cramping over to the corner there is because I want this middle space to figure out my resultants. Okay, so EX totals. Okay, so my EX, I guess I could have started with XY, it doesn't really matter. Okay, so I've got 9.44 to the left and 9.00 times 10 to the 6 to the left. So really what's going on here, sorry, 9.00, yeah, okay, we're good. All right, so these two x's, because they're going in the same direction, they just add together. So 9.44 times 10 to the 6th newtons per coulomb plus 9.00 times 10 to the 6th newtons per coulomb. Okay, so the x's, when those add up, I end up with 1.84 times 10 to the 7 newtons per coulomb left. Now for the EYs, though. Those are going to be a little trickier. Okay, because the EY from A, that's directed down. So we're going to make him negative 7.08 times 10 to the 6th newtons per coulomb down. So that's why it's negative. And then the EY is positive because he's going up. So 1.20 times 10 to the 7 newtons per coulomb up. Now hopefully you understand what's going on there, because this guy, he's going down. This one's going up. Because they're going in opposite directions, we have to subtract. Okay, and when we do that, the y totals, okay, so that one works out to 4.90, remember using all your digits, times 10 to the 6th newtons per coulomb up. Okay, so at point P, we are going left and up. So at point P, we have a net electric field going left, 4.90, whoops, that's the X, make sure we get them straight, it's easy to mess this part up. So 1.84 times 10 to the 7 newtons per coulomb. Okay, and then we're going at 4.90 times 10 to the 6th. There we go, newtons per coulomb. Draw that a little bigger, just, okay. It's not quite to scale anymore, sorry. Not that it was before either, but that's okay. So now we have to figure out the resultant. Okay, so ER, okay, and then squared, because this is Pythagorean theorem. So 1.84 times 10 to the 7 newtons per coulomb squared plus 4.90 times 10 to the 6th newtons per coulomb squared. Okay, so then my ER, so the resultant, Okay, that works out to 1.91 times 10 to the 7th newtons per coulomb. Great, then I need the angle. So that, of course, is tangent. So tangent alpha, oh, I'm trying to squish this in. I'm so sorry, guys. Okay, so tangent is opposite over adjacent, so that's the 4.90 times 10 to the 6th newtons per coulomb, all divided by the 1.84 times 10 to the 7th newtons per coulomb. Okay, so that gives me an angle. Okay, where's the angle there is 14.9 degrees. Okay, so that could be left of up or north of east, that kind of thing. North of east. Okay, if we're using polar coordinates, that is here. So we go 180 minus 14.9. Which is 165 degrees. Okay, so all of those work. So our final answer, our E resultant, so I'm just going to put it right down in the corner here. I'm sorry. So 1.91 times 10 to the 7th newtons per coulomb. To the 7th newtons per coulomb. And I'm going to say 14.9 degrees north of east. Wow, that is really didn't leave myself enough space. So that could also be 1.91 times 10 to the 7th newtons per coulomb at 165 degrees, or 14.9 left of up. All of them are appropriate. That's just fine. Whew, I'm really sorry that that's so tight. Yeah. So anyways, I want you guys to practice this stuff. It's section 11.1 in your textbook. So it starts on page 553, numbers 5 through 9. You can use your textbook, or you can print the that document or those pages off from the workspace card. So thanks, guys. I know this was a little bit of a long one again. Just remember, split all those vectors up into x's and y's, and then add them or subtract depending on which direction they're going. Thanks. Talk to you later.